In our last video, we saw how we could create these unique organometallic compounds with a semi-ionic, semi-covalent carbon-to-metal bond. Now, because this bond has some ionic characteristics and a metal with very low electronegativity, this bond is going to be highly polarized towards our carbon. So we get this partial negative carbon, partial positive metal, and a very nucleophilic carbon. So in today's video, we're going to look at how that nucleophilic carbon can be used to make some interesting new reactions. Let's start out with a simple acid-base reaction. So our carbon here, of course, is highly nucleophilic because of that bond to our metal, but it's also highly basic, right? Anytime we have a large negative charge density on a carbon, it also tends to be a very good base as well. So if we put it together with water, we're going to take the electrons from our nucleophilic and basic carbon, and of course we're going to use those to deprotonate our water molecule in a simple acid-base reaction. So we'll end up producing just our propane, as we're taking this bond here and forming a bond to our hydrogen on our water instead. So we end up with our 3 total hydrogens here. We started with 2, we added on 1 more. Of course, then we get our hydroxide ion as our conjugate base of our water, and we'll have our magnesium and our bromine breaking off together as just this magnesium-bromine cation. Now, this reaction can also occur, of course, with our organolithium compounds. So let's say we have T-butyllithium. So our T-butyllithium would look like this. We'd be reacting it with water. Again, we use that polarized bond to deprotonate our water. That would create T-butane. And our hydroxide ion again. Of course, in this case, we just have our lithium cation here instead of our magnesium-based cation. This, of course, is the reaction that happens when we have T-butyllithium exposed to the moisture in the air. So this reaction is highly exothermic. It also produces an alkane, which is quite flammable, and so that's what then leads to the ignition and burning of T-butyllithium when it's exposed to air. So this is actually part of the reaction that we talked about in our last lecture that led to the death of Sherry Sonji. Now, generally, both of these reactions are going to be unintended reactions, right? This isn't really a reaction that we want to happen. It's taking our valuable organometallic compound and it's making a relatively unreactive alkane, except for, of course, the combustion reaction, which we generally don't want to occur, at least not in our typical lab settings. So, for the most part, we usually don't want our organometallic compound to react as a base. So what that means is we want to avoid water with all of our organometallic compounds. And so we're usually going to always keep them in solvents like ether, where we can have that completely anhydrous or without water, and we don't have to then immediately lose our organometallic compound in this acid-base reaction. So this is generally not a favorable reaction for us. Again, because it's really just taking that very reactive compound and making something that isn't particularly useful to us as organic chemists. One of our more useful reactions with our organometallic compounds is using that organometallic compound as a nucleophile to attack a carbonyl. So in this reaction, we're going to use a carbonyl. Again, my R groups are just indicating any kind of carbon chain here. So our carbonyls are carbon with a double bond to oxygen. We're going to react it with our organometallic compound, such as our Grignard reagent. And we're going to do this in 2 steps. First, in the absence of water, so using something like ether, where we can eliminate all of our water present, again, because that water would react with our organometallic compound. And then we'll use a second step where we're going to add acid in order to get our final product. So it's going to add our carbon group as a nucleophile to our carbonyl. So we're going to end up producing an alcohol as we add on the new carbon group from our organometallic compound. And of course, we'll also release our magnesium bromide cation. Now let's walk through the mechanism of this reaction using our 2-butanone compound shown here and our ethyl magnesium bromide compound here. So with our carbonyl compound, we have our carbon double bonded to our oxygen. The oxygen, of course, is more electronegative. So we have this polarized bond with our carbon acting as our electrophile. Of course, as we know, our organometallic compounds have that strongly nucleophilic carbon. So our reaction is just going to start with our strongest nucleophile attacking our strongest electrophile. So we can take this bond, move it up here, and attack that electrophilic carbon. Now at this point we would have 5 bonds to that carbon, so we also need to break a bond here as we're forming that new bond. Our oxygen, of course, is already pulling those electrons toward itself. It already wants those electrons, so it's easy enough to just move our electrons up onto that oxygen to make room for a new bond that's forming. So after this first step, we'll have our original 4 carbons, and then we'll have just a single bond to our oxygen now with a negative charge. And we'll have our new bond down here to our 2 carbons of our organometallic compound. So we just have our 2 carbons here. And then of course we have our positively charged magnesium bromide, which we'll kind of tend to associate with our negatively charged oxygen here. So that's our full first step in the presence of ether. Now we're going to take this ionic compound, our alkoxide, and we're going to put it with our acid. So now we're starting our second step with our acid here. So there's our hydronium ion. Of course, this acid could come in the form of a variety of different acids, hydrochloric acid, sulfuric acid, whatever your particular preference is there. So now we have our strongly basic alkoxide and our acid, and we're going to react in a simple acid-base reaction to produce our alcohol product. So we pull off that hydrogen from our acid, produce our water molecule, and so now we have our alcohol produced, and of course we have our byproducts of water, and of course our cation from our organometallic compound. So overall we're able to take a carbonyl and create an alcohol from that carbonyl, but of course the most exciting thing that we're doing here is we're able to add new carbons onto our existing carbon chain. Right? So again, what we've seen before is that it's actually somewhat difficult to add on more carbons to a structure because of course carbon-carbon bonds are relatively stable and can be hard to form. So it's very valuable to have these sorts of reactions where we're able to then add on additional carbons here. Right? So we started with a 4-carbon molecule and we end with a 6-carbon molecule as we add on the 2 carbons from our Grignard reagent. Again, of course, here I'm showing this with my Grignard reagent, but we can do a very similar reaction with our organolithium compounds as well. So it wouldn't really change the mechanism at all. It would just be changing what exactly our organometallic compound looked like. Now you might have noticed that so far we've been working almost exclusively with alkali metals. So why are we avoiding that big block of transition metals in the middle of the periodic table? Well, these transition metals actually are incredibly useful for organometallic reactions. However, they behave quite differently due to the extra electrons that are available in those d orbitals. So when you look at a transition metal such as iron, so of course for transition metals we have our s block of electrons, right? So we can have 2 electrons in the s block. We also have our p block, which can fit up to 6 electrons, but we also have our d block available that can fit up to 10 electrons. Now for most of our atoms, we've looked at the octet rule, where we're really just looking at filling the s and p subshells to get our full outer layer of valence electrons. Right? So the octet rule comes from the fact that a lot of our atoms are trying to fill these up so that they have that full outer layer of electrons. For our transition metal elements, we also are trying to fill up our d subshell as well. So instead of an octet rule, we get an 18 electron rule, where we want to get our 18 electrons in order to fill up our full valence shell of electrons. Now for most of our metal compounds, of course, as always, they have very low electronegativity. So they're generally going to be cationic or Lewis acids. Right? So our iron will act as a Lewis acid, and then it's going to interact with Lewis bases that will donate electrons to our metal in order to form what we call coordinate bonds. So our coordinate bonds will form from donations of lone pairs to be shared with our metal. So we have a lone pair shared from Lewis base to our Lewis acidic metal. And our goal is going to be to form these coordinate bonds between our nonmetals and our metal in order to form this transition metal complex where our metal has this full 18 electrons. One important biological example of this sort of transition metal complex is in our heme group inside of our hemoglobin proteins. So our iron normally has 8 valence electrons. When we have an iron 2+ cation, such as in our heme group here, that means that we'd have 6 electrons here for our iron. So we've got our 6 electrons. We want to get up to 18 electrons for our 18 electron rule. So we have it surrounded by these 4 nitrogens in this ring structure here. Each of these nitrogens are able to share 2 electrons with our iron. Right, so we've got all these electrons here. So we have this, this is called a porphyrin ring that kind of surrounds and bonds to our iron there. And then we have 1 nitrogen from below that comes up and interacts with our iron as well. So we've got surrounded by these 5 nitrogens that are bound up within our hemoglobin protein. And then we bring in our oxygen molecule, and our oxygen can share 1 lone pair with our iron to get the final 2 electrons that we need to fulfill our full 18 electron rule. Right, so we've got our 6 electrons of our iron initially, and then we're adding 12 more to get to that full 18. Now, of course, in our body, this transition metal complex is incredibly important because it allows us to bind our oxygen within our hemoglobin protein, and then that allows our hemoglobin, of course, to carry oxygen through our blood and release that oxygen throughout our body. Right, so this is actually how oxygen gets delivered to our cells, is using this electron rule and this transition metal complex. Now there are a bunch of different ways that we can use these transition metal complexes in our organic chemistry. We're going to look at just a couple different examples today. This is a very active area of research though. There's a lot of different ways that we use these in modern organic chemistry. So first we'll be looking at our Gilman reagents, which is a copper-based transition metal complex. So we're going to start with our copper halide. Again, of course, X is just representing any halogen here. So we're going to be combining our copper halide with our organolithium compound. We're going to exchange our alkyl group here for our halogen. So we end up creating a alkyl copper compound, and we also create our lithium halide ionic compound. Now if we add another unit of our organolithium compound, we're going to again exchange that alkyl group and give it to our copper, but in this case, of course, we don't have another halogen here. So we're going to end up forming, this is copper compound, where we have our 2 alkyl groups attached to that copper. This is going to be a negative anion overall. as well as our lithium counterion here. So we get this lithium and copper complex, and this is what we call our Gilman reagent. So our end product here is this Gilman reagent, where our copper has our 2 bonds to our carbon groups, and is a negatively charged group then interacting ionically with our lithium counterion. Now, if we look at our copper here and compare it to the 18 electron rule that we learned before, so normally copper starts with 11 electrons, if we look at the periodic table. In our copper-lithium compound here, our copper has an oxidation number of +1, because it's bonded to that more electronegative halogen there, which would then get a -1 oxidation number. So with that +1 oxidation number, our copper is giving away an electron to have 10 total valence electrons. So we have 10 valence electrons around our copper. We have 2 bonds here to our carbon groups that each are contributing 2 electrons. And so overall, around our copper, we have 14 total electrons. This does not fulfill our 18 electron rule, so we say that our copper is unsaturated in terms of our coordinate bonding here. It's coordinately unsaturated. So our Gilman reagent then is going to react, and as part of this reaction it's going to want to try to gain extra electrons in order to fulfill that 18 octet rule. So we're going to use this and the nucleophilic nature of our carbon bonds here to react in what we call a cross-coupling reaction. So in our cross-coupling reaction, we're going to take our Gilman reagent. So we have our lithium and copper complex here. And we're going to react it with a alkyl halide, which note this can be an sp or sp2 hybridized alkyl halide in this case. This isn't a typical SN2 reaction. Our Gilman reagent and our alkyl halide are going to combine together to form this intermediate where we have a saturated copper transition metal complex. So it's actually going to add in between our alkyl halide bond here. So we get our 4 bonds now to our copper, creating the full 18 electrons around our copper. So that acts as kind of the driving force toward this transition state. But then this will break apart and we'll create we'll get a alkyl copper compound. We'll get a combination of 2 of our carbon groups, right? So we'll be combining one of our carbon groups from the alkyl halide together with one of the carbon groups from our original carbon groups that were attached to our copper. And then we also produce our lithium halide ionic complex. So we kind of use that unsaturation of our copper to temporarily create this transition state, and then we end up cross-coupling in our products where we're switching the alkyl group that's attached to our alkyl halide with one of the alkyl groups that's attached to our copper. Let's look at a specific example now. So let's say we have our lithium Gilman reagent complex. So we have our lithium. I'm going to use a ethyl group in my Gilman complex. So I have my negatively charged anion here with my copper complex. I'm going to react it with a alkyl halide where my chlorine here is actually attached to a carbonyl. And again, remember this does work because we're not following a typical SN2 reaction, and so it doesn't really care about the hybridization there. So we're going to be cross-coupling here. So we're taking one of these carbon groups and attaching it on where our halogen was. So that gives us the same basic structure, but then plus 2 more carbons. Right, so we'd end up with this compound here as we couple those carbons together with the carbons from our alkyl halide-based compound. We end up with our copper still remaining bonded to 2 of our carbons, and then we have our lithium chlorine ionic compound produced from our lithium combining with that chlorine that's lost from our alkyl halide-based compound. So again, it provides us with an interesting new way to create carbon-carbon bonds using the nucleophilic carbons in our organometallic complex. Now these cross-coupling reactions are actually quite common. We can use a variety of different transition metal complexes to do slightly different cross-coupling reactions, but that's actually beyond the scope of this course. So this Gilman reagent is just one example of some of the many different cross-coupling reactions we can do with these sort of complexes. One final example of a transition metal complex catalyst that we'll look at is Zieglers catalyst. So this uses a unique mechanism where we have a zirconium ion that is then interacting with the pi electrons from two different aromatic rings. So we have these two cyclopentadienyl anions here, where we have an aromatic compound formed from two double bonds combined with two electrons from an anion. Right? So each of these have 6 electrons in this conjugated pi aromatic system. We have, of course, 2 electrons from each of these chlorines, and we're actually sharing these 6 pi electrons with our zirconium ion here. So it's not just interacting with a single lone pair, or it's not just a single covalent bond. It's actually sharing electrons with the pi electrons of that conjugated aromatic ring. Remember, those electrons kind of make a cloud above and below the ring system, and so we can just take that ring and kind of stack it up here against our zirconium ion and allow those electrons to interact with our metal here as well. So it's actually sharing all 6 of those electrons from each of those. Our zirconium atom here actually starts with 4 valence electrons based on its position on the periodic table, but it forms a 2+ cation, so it has 2 less electrons here. So we've got our 2 electrons from around our zirconium atom itself, sharing 6 each with these aromatic rings, 2 each with these 2 chlorines to get our full 18 electrons. So again, 6, 6, and 6 makes that 18 electron rule fulfilled. We can use this zirconium complex to catalyze an interesting polymerization reaction. So if we remove these chlorines and instead coordinate our zirconium with the pi electrons of a double bond, since we're going to be pulling electron density away and sharing it with our zirconium ion, we essentially make our alkene here more electrophilic. Right? So our alkene becomes more electrophilic. We can bond another carbon group on here, and of course, as always, this carbon becomes nucleophilic because it's more electronegative than our metal ion here. So we have a nucleophilic carbon and an electrophilic carbon. So then we're going to be essentially attacking our carbon onto that alkene, and we can end up then creating a longer chain of carbons. If we repeat this multiple times, we can do a polymerization reaction catalyzed by this transition metal complex. This is referred to as Ziegler-Nada polymerization. So this represents a new mechanism for forming polymers without using that typical free radical polymerization mechanism that we've seen before. So what we see here is that we're able to use a wide variety of different organometallic compounds to create varying carbon-carbon bonds in a variety of different scenarios. So these are incredibly useful compounds because, again, it's relatively hard to make those carbon-carbon bonds. We've really just touched the basics of these organometallic compounds. There's a bunch of other organometallic compounds that are commonly used as well, but again, we just don't have the time to go over all of those. As we've seen, they're also very important biologically as well. We see a lot of different transition metal complexes that are used to catalyze different reactions in the body, or of course, in the example of heme, it's able to coordinate to the oxygen so that we can carry that oxygen through our body, so all of our cells get the oxygen that they need to live. So organometallic compounds continue to be a very active and important area of study, both for organic chemistry and biochemistry.